Hello everybody, this is Homer White back again with part 2 of our third chapter in the course on the relationship between two factor variables. In this part of the course, we're going to start looking at the inferential aspects of a research question. We're going to look at a formalized test for inference called the chi-square test that's used to see whether there is a relationship between two factor variables. And we're also going to look at particular ways of computing one of the numbers that goes along with a test of inference. It's called a p-value. Now always remember to make sure that the necessary packages are loaded. Okay, what do I mean by the inferential aspect of a research question? To get a handle on this, let's take a look at a new data frame, a somewhat small one, called LegJump. It's based on some real data, and you can learn more about it by running the usual data and view commands to get a close look at it, and also the help command in order to find out more information about who collected it and why. The data are from a study by Leon Mann, a social psychologist who published an article in 1981. Dr. Mann was interested in what kinds of factors might influence the behavior of crowds that gather to watch a person who's on a high ledge or other structure and is threatening to jump off of it. A suicide attempt, basically. Now, before we go much further, let's just assume that none of the incidents in this study ended badly. After all, the firemen usually come pretty quick, don't they? And they have those trampoline-type devices that the jumper could land in rather than falling on the pavement. And I imagine pretty quickly the jumper's spouse or minister or psychotherapist would emerge on the scene and lean out of a nearby window and talk the jumper back inside. So let's just optimistically assume that nobody died so that we can contemplate this data set with a little bit less anxiety. So with that in mind, do take a look at the data set. You'll find that the data frame has 21 rows. Each row is an incident in which someone was threatening to jump off of a ledge or high structure. These incidents were in the United Kingdom probably in the late 70s. There are two columns in the data frame. These are the two variables that are measured on each incident. One variable is the weather, and the values are warm and cool. The incident took place during either a warm month or during a cool month of the year in England. The other variable is crowd behavior. The crowd was either polite, thus quietly milling about perhaps, waiting for the incident to resolve itself. Or the crowd might have been baiting, yelling things at the jumper. Go ahead, jump, will you? That sort of thing. You imagine them having English accents, just generally being rude to the jumper. What we've got here are two factor variables, weather with the possible values warm and cool, and crowd behavior with the possible values polite and baiting. And our research question is about the relationship between these two factor variables. Does the weather have any effect on crowd behavior? Does it make a difference in how the crowd is likely to behave? Now we know how to examine these relationships in data. We need to make cross tables, so we pull out our xtabs function and we apply it with the usual formula data input. We think of weather as the explanatory variable. It might have some impact on the crowd's behavior. We think of crowd behavior as the response variable, so we put it second. We create the two-way table. We put it in an object that I call WeBe. That's just short for weather behavior, I guess. And if you print out WeBe, then you get to see your two-way table. 2 rows, 2 columns, because each variable had 2 values. And so there are 4 cells in the table, and we see the observed counts in each of these cells. Of course, the counts don't answer the research question for us. We need to compare conditional distributions of one of the variables in terms of the possible values of the other. So we try some row percents. And this gives us the conditional distributions of crowd behavior given that weather is cool, that's this top row, and the conditional distribution of crowd behavior given that weather is warm. And we see right away that these two conditional distributions are quite different. For example, if we were to compare row percentages going down the baiting column, of the times that the weather was cool, only 22% of those times did the crowd bait. But when the weather was warm, the crowd baited about 67% of the time. That's a huge difference in row percentages, so there's definitely a relationship in this data between these two factor variables. It basically looks like crowds were nastier in the warm weather. But this brings us to the inferential question. We've got this pattern in the data, but is that pattern in the data due to a real association between weather and crowd behavior? That is, does weather really influence crowd behavior? Or could that pattern in the data just have occurred by chance variation in the way that the incidents worked out? Now, what do I mean by that, chance variation? Well, when you think about it, there are lots of things besides weather that might affect crowd behavior. For example, how long the incident lasts. My intuition suggests that the longer the crowd has to wait around, the more impatient some of the crowd members may become, and the ruder and more impolite they might be towards the would-be jumper. The number of people in the crowd probably has some influence on the crowd behavior. The more people there are, the more likely it is that some of those people will be especially impolite sorts of people who yell rude things and make other people yell around them. Or if you just happen to have a high percentage perhaps of rude personalities amongst the onlookers, then that would increase the chances that the crowd would get into a baiting mood. I hate to say this, but maybe even the personality or behavior of the would-be jumper could be a factor. Maybe an especially dorky or awkward jumper might draw out various kinds of impolite behavior from a crowd that ordinarily wouldn't be so rude to other sorts of jumpers. So all of these things, the things we have listed, and many other factors that we haven't thought of yet, vary from one incident to another, even if the weather is the same. If on a given cool day there's a ledge jump incident, even if we keep the weather cool, the length of the incident, the number of people in the crowd, the personalities of those who gather, and so on, can vary. And we model this variation as chance. So if you think that weather has no influence on crowd behavior, then you think that chance variation and all of these other factors could account for the kind of two-way table that you saw and the difference between those conditional distributions that you saw. If you think that way, if you think that weather and crowd behavior are not related, then you're a supporter of what we call the null hypothesis, or H0 for short, H with a 0 subscript. So this is the claim that weather and crowd behavior are not related. Now, opposed to that is the alternative hypothesis, or H sub A for short. This is simply the claim that weather and crowd behavior are related. It is not the claim that weather is the only thing that accounts for crowd behavior, but just that there is some relationship, however slight, between weather and crowd behavior that's a real relationship out there in the structure of the world. Now, the null thinks that the relationship we saw in the data occurred just by chance variation in all of those other factors that influence crowd behavior, but not weather. The alternative thinks that the relationship in the data is too strong to be explained just in terms of chance variation in those other factors, that weather has to have something to do with it. So how shall we resolve the dispute between these two hypotheses? The way we do it is by an interesting chain of argument. And I'm going to outline it here, and then we'll go carefully through the chain of argument once, but we'll repeat it a great many times and look at it from different points of view, because it really is quite a bit to take in all at once. What we're going to do is temporarily, and for the sake of argument only, assume that the null hypothesis is right. We're going to assume that there's no relationship between weather and crowd behavior, that the weather makes no difference. And we're going to find what we would expect to see in the way of a two-way table if these two variables are completely independent. Then we're going to find a way to numerically measure the difference between the table that we actually saw, this one, and the table that we would expect to see if the two variables were unrelated. And then we'll find the chances of getting at least that big a difference if the two variables are unrelated. Now, if that chance is small, if what we've got here is a difference that's unusually big, if the null is right, then this difference that we see is actually unlikely to occur if the null is right. And that's evidence against the null. On the other hand, if these chances are not too small, then the table that we see is not much evidence against the null. That's the basic outline of the reasoning. But let's go through it in detail here. So, if you believe the null hypothesis, you think that weather makes absolutely no difference to crowd behavior, then you're in a position to be able to estimate how the chances work for all of those other factors that you think might affect crowd behavior. That is, you can make an estimate, based on the data you've got, of the chance that a crowd in general would be baiting, and an estimate of the chance that a crowd in general would be polite. Again, regardless of the weather. Here's how you do it. You notice that there's 21 incidents in all, and that in 10 of those cases, the 2 here and the 8 here, the crowd was in a baiting mood. In 11 of those incidences, the 7 and the 4, the crowd was polite. Now, 10 out of 21, if you multiply it by 100 to make it a percent, gives you 47.6%. So 47.6% of the time, the crowd was baiting in the incidents that we got to study. That's our best guess, as believers in the null hypothesis, that's our best guess at the chance that a crowd in general would be a baiting crowd. We just take the percentage of times that crowds that we saw were baiting and use that as our estimate. Similarly, 11 times out of 21, the crowd was polite. Now, if we do 11 divided by 21 times 100 to make it a percent, we get 52.4%. That's our best guess at the chance that a crowd in general would be polite. Now, let's apply this to see what kind of two-way table the null would expect if there were 21 incidents under study, some of which were in cool weather and others which were in warm weather. Again, here's our two-way table. Notice that 9 times we had cool weather and 12 times we had warm weather. What kind of table would we expect to see if we had 21 incidents, 9 of which were in cool weather and 12 of which were in warm weather? Let's think it through. So we have cool weather 9 times. Now the null expects that at about 47.6% of those 9 times the crowd will be baiting. If you pull out a calculator and take 47.6% of 9, you get about 4.28. So for a cool weather in a baiting crowd, where we see a 2 here in the table, the null hypothesis would expect to see about 4.28, give or take some for chance variation, in the way that all those other factors, besides weather, come out. Now, as for politeness, the null would expect that 52.4% of those 9 times, the crowd would be polite. That turns out to be 4.72. So, where we actually saw 7 incidences in which the weather was cool and the crowd was polite, the null hypothesis would expect to see about a 4.72 there, give or take some again for chance error. Now let's focus on the warm weather. So the weather was warm 12 total times, 8 plus 4. Now the null expects that about 47.6% of those 12 times, the crowd would be baiting. That's 5.71. So where we see an 8, the null is expecting to see about 5.71. Now, it expects to see politeness 52% of the time, and so 52% of those 12 times, the null expects to see politeness. 52% of 12 is about 6.29. So that's the number that the null expects to see in the place where 4 actually occurred. So what we've got here is a table of expected cell counts. The null expects to see a two-way table that would be about like the one displayed here, with the expected counts put into it. Give or take some, I must stress, for chance variation in all of the factors besides weather that might affect crowd behavior. Now, I know you're probably thinking to yourself, those numbers, they're all fractional. There's no way you could ever have 4.29 baiting cool weather crowds, and that's true. The 4.29 is just an expected value. You're expecting 4.29 give or take some for chance error in that cell. The actual values, of course, will be whole numbers that depend on chance. But this is about the table that the null expects to see. I would like to point out that you don't have to reason your way slowly in order to find all of those expected counts. There's actually a formula that gives you all of these answers quite quickly. The way to find the null's expected counts in a table is to take the row sum for the cell, the column sum for the cell, and divide by the total counts, which is called the grand total. So for example, the cool baiting cell, where we actually saw a 2, here's how you would find the null's expected count. You would look at the row sum, the 2 plus 7, here it is. You would look at the column sum, the 2 and the 8, and here it is. You would multiply them together, and you would divide by the grand total, the 21 incidents. And that does work out to about 4.29. So that formula can always be applied to quickly find the null's expected counts, and that's good in case you happen to have a rather large two-way table with lots of cells in it. So let's take stock of where we are so far. We observed this two-way table. If the weather and crowd behavior have nothing to do with each other, you expect to see about this two-way table. The difference between the two of them, just taking the observed and subtracting off the expected, gives you this two-way table. What we would like to do is to find one number that describes how much the observed table differs from the expected. That is, one number that sort of describes how different these four numbers are from 0. Statisticians have a proposal for such a measurement. They call it the chi-square statistic. Although it's written rather like an X, that's the Greek letter chi, and here we have chi-squared. Here's the formula for it. To find the chi-square statistic, for each cell, you take the observed count that you actually saw, you take the expected count, what the null expected, you look at the difference, and you square that difference. That's why it's called a chi-square statistic. You divide by the expected count for that cell. You do that for every cell in your two-way table, and then you sum those fractions over all of the cells in the table. So how does that work out in this particular example? Well, our two-way table had 4 cells, so there's going to be 4 fractions to work with. The actual 2, the expected 4.29, square, divide by 4.29. And you work the same way, actual minus expected, squared divided by expected, for each of the 4 cells. If a calculator add them up, it turns out to be about 4.07. That's the chi-square statistic. That number measures how different the observed two-way table is from the expected two-way table. The bigger that number is, the more the observed table differed from what the null expected. The bigger that number is, the more surprising the results are to a believer in the null hypothesis. Now, the chi-square statistic is always at least 0. It makes sense because you square those differences. So even if they start out negative, you'll get positive numbers in the end. And as we just said, the bigger the chi-square statistic is, the more the data differ from what the null is expecting. The really big question here is, what's the chance of getting a 4.07 or more, like what we got, if the null is right? This chance is called a p-value. P is short for probability or chance. We're going to find a way to estimate this p-value. And our strategy is going to be simulation. What we're going to do is repeat the study many, many times in a situation where the null is guaranteed to be correct. Now you might wonder how we could do that. Do we have to go looking around for sets of 21 actual ledge jumping incidences? And if so, probably have to wait a long time before we get 21 of them together. And how could we guarantee that the null would be right in those situations? After all, what if the null is wrong and weather does influence crowd behavior? We'll never be able to repeat the study any times in a situation where the null is correct. So what we actually do is we have a computer simulate repeating the study many times. And we set the computer up in the situation where the null is correct. We make the computer imagine a world where the null is correct. And we have it repeat this 21 ledge jumping incidence study many, many times. We'll compute the chi-square statistic each time. And we'll keep track of how often that chi-square statistic exceeds the 4.07 that we actually got for a chi-square statistic in this study. The p-value, the chance of getting a 4.07 or more, is approximately the proportion of times that the simulated chi-square statistic exceeds 4.07. So how should we do the simulation? There's a Manipulate app in the TigerStats package that'll help you do it. To make sure that the Manipulate package is loaded, we'll require Manipulate as our first line of code. And then we'll bring on the function chi-square-sim-slow. Notice that it follows formula data input. You simply put in the weather, the twiddles weather plus crowd behavior. Your data is ledge jump. And there's an extra argument called effects equals fixed. And this is going to set things up so that although there's 21 incidents each time you go back and repeat the study, 9 of them will be in cool weather and 12 of them will be in warm weather, just like they were in the actual study. So we'll copy this and go back to RStudio and paste it into the console and give it a try. And increase the size of the screen just a little bit. Now let's see what we have down in the let's see what we have in the screen first. We have some bar charts that give a graphical picture of the two-way table itself. And so according to the legend, the red bars stand for baiting crowds, and these light blue bars, I guess, stand for polite crowds. And we see again that when the weather was cool, the crowd was usually polite, but when the weather was warm, the crowd was usually baiting. Over in the console, starting here, we get some introductory information. It first gives us the two-way table for the study, the one that we're familiar with by now. And then it says, if there's no relationship, then the expected counts are, and look at that, it gives the expected counts that we've already computed. So it's saying, here's what you would expect to see if the null hypothesis were right. It tells us the observed value of the chi-square statistic for the actual two-way table in the study, 4.07. And then it says, would you like to repeat the study? Now you have options to either do it slowly or quickly. And I think I'll go for a fast sample. So I'll enter an F, press enter, and look what happens in the console. All in a flash, R repeated the study in a situation where weather makes no difference to crowd behavior. So it's in a situation where 47.6% of the time a crowd would be baiting, and 52.4% of the time a crowd would be polite. It tries out 9 cool weather incidents, and it tries out 12 warm weather incidents, but the chances of baiting and polite are the same in all of those incidents. And it gets this table. It then computes the chi-square statistic for this table, the difference between what a null hypothesis believer would expect and what this table actually came out to be. And the chi-square statistic turned out to be 0.58, considerably smaller than the 4.07 that we got. We're informed that the total number of resamples so far is 1. That's true. We've only repeated the study once. So the percentage of times that the resampled statistics have exceeded the observed chi-square statistic of 4.07 is 0%. Now let's go over to the graph, to the plots pane. And what we see is the beginnings of a histogram, a frequency histogram for these resampled chi-square values. This little red rectangle represents the 0.58 that we got. The vertical bar here is at 4.07. So the only resampled chi-square statistic that we've gotten so far has been this one. Let's get another one. So again, we go back into this world that the computer has set up for us, where the null hypothesis is true, and we repeat the study. Let's put in F to the console, press enter. We get a new two-way table. We get a new chi-square statistic, is 0.15. Over in the plots pane, we see that the new chi-square statistic stacks up with the old one. They're about equal to the same thing. The new one here is in red. Let's start moving a little faster. So what I'm going to do is take my cursor back to the console, and I'm going to keep on entering F's to get a fast sample. But let's keep our eyes fixed for a while on the plots pane and watch the frequency histogram of the resampled chi-square values begin to take shape. Ready? Here we go. So far we seem to be getting pretty small chi-square statistics. We just got one a little bit over 2. Mostly we're getting pretty small ones. Let's take a look and see what we have so far back in the console. And we see that we've taken 20 resamples so far, but in none of those cases has the chi-square statistic exceeded 4.07. Let's keep taking resamples though. Ah, look at that. We're beginning to exceed 4.07. Doesn't seem like it's happening very often, but it does seem to happen from time to time. Okay. If you keep on going long enough, eventually one of the bars of the histogram will climb high enough to get to the top of the plot menu, and then the plot will resize itself to make more room for you to keep going if you want. I'm going to go just a few more times. Tell you what, 70 is enough times. I'm getting a little bit tired. So in my 70 resamples, only 5.7% of the time did I get a chi-square statistic that was bigger than 4.07. So, I strongly encourage you to try it out for yourself and be patient and give it a good many times, 50 or 100 times if you like. And what you want to pay attention to is the percentage of times that your resampled chi-square statistic was bigger than the 4.07 that we actually got in our study. So, each of us probably got a different approximation based upon the resamples that we took for the p-value, the probability of getting 4.07 or more if the null hypothesis is right. Now, remember, if this probability is small, then that's saying that if the null is right, something very unlikely occurred. So if the probability is small, then we should reject the null hypothesis. We should decide that it's not true. On the other hand, if the probability is not so small, then our results are not so unlikely to occur if the null is true. And so our results would not provide a lot of evidence against the null hypothesis. A really common question is, how small should the p-value be before we decide to reject the null hypothesis? I'm just going to throw out a very common convention to you. It's a convention. It's not out there in nature. It's just something that people often agree to do. If the p-value is less than 5% or 0.05, then we'll reject the null hypothesis. But if it's at least 0.05, then we'll fail to reject it. That doesn't mean that we believe that the null hypothesis is true. It's just that we don't think we have enough evidence to toss it out. So in this case, the p-value seems to be rather near 5%, depending on how things came out. In your own simulations, you might have gotten a bit more than 5%, or you might have gotten a little bit less. So it's a little bit hard to say what we ought to do in this circumstance where things are so close to our conventional borderline. Let's try this whole chain of reasoning over again, but with a different data set and a different research question. This comes from the General Social Survey from the year 2002. Now, the General Social Survey is given out every 2 years. It's a massive telephone poll, and hundreds of survey questions are asked of the people who are called up. Now, not everybody is asked all of the questions, but all in all, with thousands of people involved in the study and many questions, we end up with many possible research questions about the relationship between pairs of the variables that are measured on these folks. Now, in 2002, lots of people were asked about their race. Also, lots of people were asked whether or not they own a gun. And there were plenty of people in the study who were asked both questions. So we might try to use this data to investigate this research question. Is there any association between one's race and whether or not one owns a gun? Now, these are two categorical variables. Race, in this study, had 4 possible values: African American, Hispanic, white, and then all the other races were lumped together as other. Own gun had 2 possible values: no and yes. So we can make a two-way table to study the relationship. We think of race as the explanatory variable in this situation and own gun as the response. So we put race first. And here's our two-way table. Taking row percents, we can investigate to see whether the conditional distributions of gun ownership, given the 4 possible values of race, are the same or not. Now remember, to see if the conditional distributions differ, you should look down a column and see if there are any big differences in the percentages. I'll just look down the yes column here. Well, some of the percentages are pretty close, but some of them are quite far apart, like the 21.8% is quite far from the 13%. The 38% is quite far from the 21% and even further from the 13%. So I'd say I see some pretty big differences in the row percents as you compare down the yes column. One could say very much the same thing about differences in the row percents as you compare down the no column. There are some fairly big differences there. So it looks like there's a relationship in this data between race and gun ownership. And one way to summarize it in words might be, it looks like white folks are more likely to own a gun than folks of other races, because look at this. About 38% of all the white folks owned a gun, and for other races, a considerably lower percent owned a gun. Now let's get on to the inferential aspect of the question. Sure, we saw a pattern in our data, white folks more likely to own a gun. But is that pattern in our data occurring because there's a similar pattern in the U.S. population as a whole? Or could that pattern have just arisen through chance variation in the random sampling of people to get into the General Social Survey in the first place? So once again, we have null and alternative hypotheses. The null hypothesis would be the hypothesis that says that these 2 factor variables are not related. And the alternative says that race and gun ownership are related. Once again, I invite you to try out chi-square-sim-slow in order to compute a p-value, to find the probability of getting a chi-square statistic at least as big as the one that you got in this study. Let's try it again just for a few times. So I will pull up the code, head for the console, And I need to be a little bit careful here. Notice in the console I need to quit from the previous application, so I'll press a Q. We're all done, and we see a blue prompt, ready to enter more code. Make sure that you're done with your last step before you try to do anything else. Now let's Control V to paste in the new code, and we're ready to go. In the graph window is our two-way table. And over in the console, we see the two-way table, and we see the two-way table that the null would expect. We see the chi-square statistic is about 37. And if we enter F for fast sample, then we'll begin to build up a histogram of resampled chi-squared values. So I'll just keep on taking resampled chi-square values, and you can just watch the histogram emerge. Now remember, the chi-square statistic is about 37. 37 is so big that it doesn't even appear on the horizontal axis that's provided for us for this histogram. And as we continue to imaginatively rerun the study many, many times under circumstances in the computer that guarantee that the null is correct, that guarantee that there's no relationship between these two variables, we see that we get chi-square statistics that tend to be much smaller than 37. Look at the window, it just resized itself. Check back in the console. I've done 100 resamples so far. The largest chi-square statistic that I've gotten, looking over in the plot window, is scarcely more than 10. If the null is right, the chi-square statistics look like they should be, I don't know, around 4 or 5 maybe, on the whole. Sometimes they can be larger, but not much larger and not very often. But it seems highly unlikely that the chi-square statistic could ever get as big as 37 if there's no relationship between these two variables. Let's step back for a moment and record a couple of cool and interesting facts about the chi-square statistic. For any two-way table, you can compute a number called the degrees of freedom. The degrees of freedom is simply the number of rows in the table, minus 1, and times the number of columns in the table, minus 1. Now, if the null is right, the chi-square should turn out to be around the degrees of freedom, give or take the square root of 2 times the degrees of freedom, or so. So, for example, in our study, the two-way table had 4 rows because there were 4 values for race, African American, Hispanic, other, and white. It had 2 columns because there were 2 values for gun ownership, no and yes. 4 minus 1 times 2 minus 1 works out to 3 times 1, which is 3. So if the null is right, the chi-square should be around 3. Give or take how much? Square root of 2 times the degrees of freedom. Now that's square root of 6, and that's about 2.45. So if the null is right, then you would tend to get around 3, give or take 2.45 or so. Let's look back at our histogram. Here's 3 on the x-axis, and sure enough, 3, give or take 2.45, that covers a lot of the values that we got. Now, the actual value of the chi-square statistic in the study was almost 37. That's very far above what the null hypothesis is expecting. It's a lot of 2.45s above 3. It's a highly unlikely thing to get if the null is right. So, looks like in the GSSO2 study, we have some pretty strong evidence that race and gun ownership are related in the U.S. population. The results we got are very unlikely to occur if there is no relationship. Now, this way of thinking can be formalized in a process we call the chi-square test. Let's learn about this formal process. I'd first like to point out that the chi-square sim slow app is, when you think about it, a pretty slow way to get a p-value, because you have to repeat it many, many times in order for your proportion of times that the chi-square statistic exceeds the one you observed to be a good approximation to the probability of the chi-square statistic exceeding the one that you got. So all the effort we've been putting in to chi-square sim slow has been very good at helping us to understand what to expect when the null hypothesis is true versus what we actually got. But it's not a great way to get really, really good approximations to that probability that we seek. Fortunately, mathematicians have devised other ways besides very slow simulation to approximate these p-values, and they've embodied them in what's called a chi-square test. Now, we have a version of the chi-square test called chi-square.test.gc that we'd suggest you use. It computes the chi-square statistic for your two-way table, and it approximates the p-value for you. Now, we apply these tests in 5 steps. So we're going to outline the 5 steps, starting with a new research question between two factor variables. You may recall in the Math 111 survey data that we asked people for their sex, male or female, and we asked them where they prefer to sit in class, front, middle, or back. Is there any relationship in the Georgetown College population between sex and seating preference? Can we use the data that we have from our sample to answer this question about whether there's a relationship between those variables in the population? Step 1 in a chi-square test of hypothesis is simply to state the two competing hypotheses, the null and the alternative hypothesis. Remember that the null hypothesis is always the one that says nothing interesting is going on. The two factor variables are not related. Notice how carefully it states that they're not related in the population. They're probably related at least a little bit in the sample, because two conditional distributions in the sample are highly likely to be at least a little bit different. The alternative hypothesis says that out there in the Georgetown College population, sex and seating preference are related, at least a little bit. Now, steps 2 and steps 3 are separate steps, but they're often happening in computation together. Step 2 is computation of the chi-square statistic, and step 3 is computing the p-value, finding the chance of getting a chi-square statistic at least as big as the one you got if the null is true. The way to find these numbers is to run chi-square.test.gc. You give it the same formula data input that you use whenever you're investigating the relationship between two factor variables. Now, in this case, I think of sex as the explanatory variable and seat as the response, and so sex will come before the plus and seat afterwards. And remember, Math 111 survey is the data frame where these variables reside. I'm going to go ahead and copy this code and try it out in RStudio. Going down to the console, I see I need to quit the previous app. Wait for my prompt. Paste in my code, and out comes something in the console. I'm going to raise the console up so that we can see the whole thing. The output says Pearson's chi-square test. Carl Pearson, who lived around the turn of the 20th century, was the person who developed this test. We first are given the observed two-way table, the counts. Next, we're given the counts that the null would expect to see if there's no relationship between sex and seating preference in the Georgetown College population as a whole. The next table gives the contributions to the chi-square statistic that come from each cell. So for example, in the cell that goes with females who prefer to sit in the front, we had an observed count of 19, an expected count of 15.21. If we take 19 minus the 15.21, square that, and divide by 15.21, the fraction we get is 0.94. In the same way, we get a fraction for each one of the cells of the two-way table. And when you add those 6 fractions together, when you add those 6 contributions together, you get the chi-square statistic. It turns out to be about 3.73. Now remember the cool fact about the chi-square statistic. If the null is right, it should be about the degrees of freedom in the table. Now the degrees of freedom in this table is said to be 2. That makes sense because degrees of freedom is rows minus 1 times columns minus 1. There are 2 rows. Rows minus 1 is 1. There are 3 columns, and 3 minus 1 is 2. Rows minus 1 times columns minus 1 works out to 1 times 2, which is 2. So if there's no relationship between these two variables out there in the population, we're expecting to get a chi-square statistic around 2. We got 3.73, which is more than 2, but it doesn't seem like a whole lot more than 2. The p-value tells us the chances of getting 3.73 or more if the null is right. Those chances are not so small. There's about a 15% chance of getting 3.73 or more if the null is right. So those are the 2 important numbers that we pick up off of chi-square.test.gc. Step 4 is to take stock of things. Think about your p-value and decide whether it's so small that you have to reject the null. Thus, step 4 is making a decision about the null hypothesis. Remember our convention. If the p-value is small enough, we'll reject the null. If it's smaller than 0.05, we will reject the null. But if it's bigger, we'll fail to reject the null. This time, the p-value was bigger than 0.05, so we're not going to reject the null hypothesis. Step 5 is to write out a conclusion. Well, this study did not provide really strong evidence that sex and seating preference are related in the Georgetown College population. After all, our results weren't all that unlikely if the null is true. We really didn't have enough evidence to reject the null. Notice how this conclusion is worded. It's non-technical. It didn't have words in it like p-value, or null hypothesis, or alternative hypothesis, or a chi-square statistic, or anything like that. It was worded in such a way that anyone who could understand the research question could understand this conclusion without understanding anything at all about the intervening mathematics and statistics. It's also couched in terms of how much evidence the study provides for the alternative hypothesis. When you're rejecting the null, you'll be saying that you have a lot of evidence for the alternative. When you're not rejecting the null, you'll be saying you don't have that much evidence for the alternative. We'd like to close by saying a little bit more about the computation of p-values. Let's try out chi-square.test.gc for our original rather small data frame, ledge jump. So we're not going to do chi-square sim slow. We're going to get chi-square.testgc to give us the test statistic and the p-value all in a flash. So we'll copy this text. We'll come over to RStudio. We'll paste in the code, see what comes out. And I need to raise the window just a tiny bit more. Here we go. Again, Pearson's chi-square test, but it's with something called a continuity correction, which you get whenever you have a rather small table. Again, we see the familiar observed two-way table. Here's the table of expected cell counts that we computed by hand earlier on in this video lecture. Here are the contributions to the chi-square statistic, the four fractions that you add together to get the total chi-square statistic. Now, the chi-square statistic that we get is 2.48. You'll remember that when we applied the formula literally, we got a 4.07. When you apply Gates continuity correction, you're going to get a slightly different value than the one that you got when you apply the formula as it stands. These differences are not too important to worry about, and you can just take what chi-square.testgc gives to you. Now, the degrees of freedom in the table is 1. The reason for that is there are 2 rows and 2 columns. The degrees of freedom is 2 minus 1 times 2 minus 1. That's 1 times 1. That's 1. The null is expecting the chi-square to turn out to be around 1, and it turned out to be 2.48, not much more than 1. Now, the computer makes an estimate for the chances of getting a 2.48 or more in a situation where the null is right. And those chances are not small at all. They're about 11%. So you might be about ready to go ahead and fail to reject the null. The p-value was bigger than 5%. But there's a warning message at the bottom of the screen. Let's think about it. In chi-square.testgc, some of the expected cell counts are low. The approximation of the p-value may be unreliable. Consider using simulation. The fact is that this p-value, computed here by the machine, is computed without simulation using an approximation technique that was invented by Carl Pearson precisely because computers were not around to do this kind of simulation for us. But that approximation technique is not very reliable when your two-way table is small, when there aren't that many elements to your study in the first place. And in this case, there's only 21 incidents to study. Because the two-way table has small counts, the null's expected counts are kind of small. And what happens is, if some of the expected counts are less than 5, then the machine is going to issue a warning suggesting that its approximation to the p-value is based on some methods that really aren't trustworthy for such a small table. So what should we do in the presence of such a warning? Well, we're asked to consider doing some simulation, just like we did with chi-square sim slow. You'll be glad to know, though, that you can do your simulation quite quickly. You don't have to keep pushing a button to get one resample at a time. You can get thousands of them all at once if you use a new argument to your chi-square.testgc function called the simulate.p.value argument. Here's how we'll develop the code. In the ledge jump incident, there were 21 incidents total, and we're assuming that when we go back and repeat the study, we're still going to have 9 cool weather incidents to look at and 12 warm weather incidents to look at. That's because these were the only 21 incidents that there were available to study. It's not like they were a sample out of some larger number of incidents. They were the only 21 incidents that occurred in that period of time. So we know that there will be 9 of them in cool weather and 12 of them in warm weather. There's no chance variation about that. The only chance variation is in how the incidents turned out. That's the chance variation in all the other factors besides the weather that might influence crowd behavior. So when the values for your explanatory variable are fixed like that, then when you do simulations, you want to communicate this fixity to the computer. And you do it by setting the argument simulate.p-value to fixed, which you put in quotation marks. Another argument is to say how many resamples you want. And you're free here to choose quite a large number. Generally, you should choose several thousand, and 2,500 is a pretty common choice. The argument B says how many resamples you would like to take. You can also get a graph that's rather like the histogram that you built up with chi-square sim-slow that'll show you which of those simulated p-values exceeded the test statistic and which of them did not. So putting all of these together with the regular formula data input, we copy, we head back to the console, we paste in the results, and here we go. Looking at the console, Pearson's chi-square test with the simulated p-value, fixed effects based on the 2,500 resamples that we requested. Notice there's no continuity correction here. We don't need one when we're not using those approximations that the old methods used. Here's our familiar observed counts. Here are the counts expected by the null. Here are the contributions to the chi-square statistic. And here's the familiar chi-square statistic of 4.07 that we got using the literal formula. If the null is right, we should get around 1 or so, and we got 4.07, which seems a bit high. What's the chances of getting 4.07 or more if the null is right? Apparently, it's about 5%. Now, if you were to try this out yourself, the p-value you get would be slightly different because these tests are based on random simulations. And so those simulations will differ from person to person. And so although the proportions will be rather close when you're doing so many resamples, each person is likely to get a little bit different approximation to the p-value. But I bet about all of you got something pretty close to 0.05. Let's look over at the Plots tab, and we see a frequency histogram for those chi-square resamples. There's 2,500 of them now, not just 60 or 100 like we were doing with chi-square sim-slow. But you can see that in small proportion of the times, the resampled chi-square statistic was bigger than 4.07. Now there's another way to do simulation that's appropriate when you actually are taking a random sample from some larger population. For example, in the Math 111 survey, the 71 students were a random sample from the Georgetown College population. Now when you randomly sample 71 students, it's a random thing not only where people will say they prefer to sit, but it's also random what sex they will be. Although in the actual study we had 40 females and 31 males, if we were to take another sample of size 71 at random from the population, we wouldn't necessarily get those same counts of males and females. So this is different from the ledge jump situation, where you go back in time to the only 21 incidents you have available and just watch how they play out by chance. Here, you go back to the population and grab another sample. The sex counts can vary. The sex counts will be random. So for this type of simulation, you should set simulate.p-value to random. Again, choose a large number of resamples And if you like, you can look at a graph. And of course, the formula data input stays the same all the time because your research question is still about the relationship between two factor variables. Let's give it a try. Pasting into the console, running the code. So here are our observed counts in our two-way table. Here's what's expected by the null, the contributions, our familiar chi-square statistic of 3.73. If the null is right, you should get a chi-square around 2. The chances of getting a chi-square statistic, at least as big as the one we got, if there's no relationship between these two variables in the Georgetown College population, is about 17%. In fact, look over in the Plots tab. Looks like about 17% of the area of this histogram comes after the 3.73 that's represented by this vertical line. So the results we got this time, a 3.73 chi-square statistic, are not all that unlikely to occur if there's no relationship between the two variables in the population. So it looks like we would not be rejecting the null hypothesis in this situation, and our conclusion would be that our data don't provide very strong evidence that there's a relationship between sex and seating preference in the Georgetown College population as a whole. Now, sometimes people can be in doubt as to whether it's best to use the simulate.p-value equal to fixed or the simulate.p-value equal to random. If you're ever in doubt, just use simulate.p-value to true. R will run a resampling routine of its own, different from the fixed and different from the random, but one that's perfectly respectable and will yield some pretty similar numbers. So, that's just the beginning of a lot of practice that we'll do with chi-square tests for many different research questions involving two-factor variables. Thank you for listening.